Good morning, everyone. Today we will continue with the second part of the second lecture of your course of Introduction to Measure Theory. So let's get to the blackboard. Now we will continue with a theorem. The theorem tells you that you have a measure space here. So this is the space. This is its sigma algebra, and this is a measure on the space. So we have a measure space here, and we have also some countable family in the algebra, and we have that the measure of the countable union of this family is less or equal than the value of the series of the measure of each set. So when this happens, and this happens for every measure space, we say that the measure is completely subadditive. Right, so what's different from the definition of a measure is that here we are not requiring that they are pairwise disjoint. So it is not necessary. If you have that they are pairwise disjoint, then this will be equality. But it may also happen that they may have some non-empty intersections, so this could be strictly greater than the measure of the whole union. So it's a very interesting, very important property, and we will work its proof here. So it is evident that we will try to construct from this family of sets another family of sets that is in fact pairwise disjoint, such that the union of this family is equal to the union of the other family. But this family is pairwise disjoint. So if we achieve this, then we can apply the property of measures that is completely additive, and we will have some equality and so on. So to construct this, we need to construct this other family. We will proceed as follows. Well, the first element of the family can be just the first element of the other, and we can make some graphs here to get the gist of it. So suppose this is A1, this is A2, this is A3, A4, this one is A5, and so on. So for the first element, we take this one as our B1. Now, the second element will be cannot be A2 because it will have an empty intersection, so we will consider only this part, and this part is equal to the difference between A2 and A1, right? So then we move on to, this is B2, onto the next set, which will be this will be A3, B3. In this case it's equal to A3, but in general we can say that this is A3 minus the union of A1 with A2. So just to guarantee that we are not getting any intersection with the other one, and so on. So in general we will say that Vk is equal to Ak minus the union of Aj and until the k minus 1 index from 1. Well, this if k is greater or equal than 2, and for the first one we will stick with this. So here we have constructed our desired family. So it is of course, well, we can show that given the way we constructed this family, it holds that those countable unions are equal. And why is that? Well, because first, for every k in the natural numbers, we have that vk is a subset of a k, which may be proper subset or may not be, may be equal. So this implies that the union of every vk will be a subset of the union of every ak. So this is clear. And on the other hand, we have that, suppose that we have some element, let's say we have some zeta in this countable union of a k, then this implies that there exists some index j naught in the natural such that zeta is in a j naught, but it may be not just in this particular set, but maybe in some many other sets, like it may be in I don't know, aj1, aj2, and so on. So this is just one index out of every index in which it can be included. But you know that the natural numbers are well ordered, so by the well ordering of the natural numbers, you can order these indexes and take the minimal order minimum of these sets. So if we have a set here from the naturals such that zeta is in a here, you can have the minimum of this set. So this minimum will be, I don't know, a naught. So this is from a naught. If you have, I don't know, any a minus 1 or a minus whatever, a minus p in general, zeta won't be here because a naught is the minimal index, because we are indexing with natural numbers in which zeta is included in. So if this is the minimal index, then we have that zeta is here and zeta is not in a k for every k less or equal than -1. Alright, unless of course a now is equal to 1. But if a now is equal to 1, then you know that a1 is equal to b1, so you will have that zeta is in v1, so zeta is also in the union of every v. So that will solve this case. And for the other cases in which a naught is greater than 1, we have that zeta is also in v a naught. And why is that? Because this term here is equal to ai naught minus the countable union, the finite union of these sets. But you know that zeta is here and zeta is not here by our by our choice of the index, by the well ordering. So given that zeta is not in this union, then zeta will still be in this set. All right, that's kind of clear. So we have that zeta is also in v a naught, and from here it follows that, well, it follows that is in the countable union of every vk. So to summarize this, we have proven that this countable union is a subset of this one, and from here we have the desired equality. So we have proved this part. All right. So since we have a family that is a pairwise disjoint, we can apply the subadditive, the additive property of measures. So we have this here, and this is equal to this, and this is equal to this, because they are pairwise disjoint and the measure is completely additive. So now what happens with the measure of every vk? We don't know if this measure is finite or infinite, I don't know, but we do know that it happens that vk is a subset of ak in general. So in the previous video we talked about how this implies that the measure of vk is less or equal than the measure of vk. So regardless if those measures are finite or infinite. So this every term of this series is less or equal than this other term. So this is less or equal than this series here. And that proves the theorem. So that shows that the measure is also completely subadditive. So when you have a family that is not pairwise disjoint, you can still apply this property. And the equality is held whenever it is pairwise disjoint. So this is a nice generalization of the additive property of measures. So from here we have a corollary. Let me write it here. The corollary tells us that if we have a measure space here, and this is some countable family of the sigma algebra, such that the measure of every k is equal to 0, then the measure of the union of every ak will also be equal to 0. So that's perhaps kind of trivial, but this follows from our proposition, from our theorem, because every element here will be 0. So this measure, you know that measures are always greater or equal than 0. So this whole series will be 0, and then the measure of the union will be 0, necessarily 0. So it is a nice generalization. I mean, without this property, this thing that it's kind of obvious, apparently obvious, would be much harder to prove. And it is the subadditive property that makes this corollary almost trivial. So there's that. All right, so another theorem. Now regarding the limits of sequences, we have our measure space here, and once again some countable family here, and it holds two properties. The first is that if this family is increasing, I mean that if this happens, it is increasing, then the limit of this sequence when k goes into infinity is equal to the measure of the union here, and this is also equal to the measure of the limit of AK. Now the second property is that if we have a decreasing sequences, and by that I mean that A1 is greater than A2 and so on. So if the sequence is decreasing and the first element, the measure of the first element is finite. So if the measure of this is finite, then the measure of everything is finite, right? So yeah, this implies that the limit of the sequence of numbers, well, not necessarily numbers, some of those could be the infinity. Well, here not. Here this is a sequence of numbers. This is really a sequence of numbers. All right, so this is equal to the measure of the intersection. And this is equal to the measure of the limit of AK. So first, some comments. You know that we proved it in the first lecture that when you have an increasing sequence, the limit of this sequence is equal to the union, right? So these limits exist because the limit of the supremum is equal to the limit of the infimum, and they both are equal to this thing here. And the same happens when you have a decreasing sequence. This limit exists and it is equal to the intersection of every element. So we will only need to show that this other equality holds. And similarly above, we will work on this part here. All right, so the proof is as follows. At first, it's when you have these sequences of family of sets, I mean, it always pays off to start with a graph. So let's draw it. In the first case, it is an increasing sequence. So perhaps this will be our A1. This will be our A2, this is A3, and so on. As previously, we wish to construct some pairwise disjoint family out of this, but that is, I mean, kind of clear that who's gonna be V1, who's gonna be V2, and this is of course gonna be V3. So it's the same procedure as the previous case. Let me write it here. V1 is A1, V2 this time is A2 minus A1. This is equal, the same as before, but for V3 we won't need to make the union of every A2 and A1. Just subtract the elements of A2. And this is because it is an increasing sequence, so A2 already contains everything that was before A2. And in general, Vk will be equal to AK minus 1 whenever k is greater or equal than 2. So these two terms here define our family, and this will be a pairwise disjoint family. So this is pairwise disjoint. All right. So we can apply. We wish to prove. Let me copy this here. This is what we want to prove. So yeah, we wish to prove this here. Let me add the brackets. So perhaps it won't be easy to start with this side of the equality. It is we are more familiar with this part. We kind of know what to do here. So this is equal to the measure of of this union by the same reasons as the theorem before. And so this method is completely additive. So this will be equal to the series of here. So now you know that this series, this infinite sum is in fact equal to the limit of as k go into infinity of finite sums. Perhaps we can write here until. All right. So this is the definition of an infinite summation, right? And given that this is a pairwise disjoint, if every vk is pairwise disjoint, then this is equal to this finite union. So this is a property that we showed before. So this is the limit here. But something interesting happens, and that is if you unite every vk from 1 into n. Let's see here. If you unite v1 with v2, the union is equal to a2. And also if you unite a b1, b2, b3, the union will be a3. So in general, this union will be equal to an. And this completes the proof. So let's change from n to k, and this will be ak. And so this is what we wanted to prove. So the equality holds. Alright, so that was for the first case. Now we have a decreasing. Let's work with a decreasing sequence. Let's, as always, start with a graph. And second part. So this is a1, a2 will be a little smaller, a2, a3 here, and so on. So the choice is, once again, easy to do. And our v1 will be this part here, this is v1, this will be v2, and so on. So v1 will be equal to a1 minus a2, and v2 will be equal to a2 minus a3. So in general, vk will be equal to ak minus ak plus 1. So yeah, this holds for every k here. So let's highlight this here. And well, this is for every k. So yeah, then this is the our pairwise disjoint family, and we have the union of every vk is equal to the union of every ak. So we can already start to prove it like this. This shall be equal to of and in fact you can already, I mean, no, it's okay, this is not, yeah, it's okay. So the procedure is kind of the same as previously. It's everything is the same, because we will have, I mean, every step is the same. The only thing that we perhaps need to show is that in here that this is equal to an. Perhaps this doesn't happen. I think this may not work. So what happens here when we have the union of every vk here, the union won't be equal to an. I think this is where it gets messy, I think. So yeah, we cannot use this way to show it. All right, so let's do another thing. Let me rewrite this. So what happens if we fixed the first? This is alright, but what happens if b2 is equal to a1 minus, or perhaps like this? This shall be the empty set, and then b2 is equal to a1 minus a2, and so on. So vk is equal to a1 minus ak. So what happens here? We will have then, so let's see what this means on the graph. So b1 will be the empty set, so v1 is nothing. v2 will be this part as before. This will be v2, but then v3 will be a1 minus a3, so it grows a little more. So v3 will be this whole area, and so on. So now this family that starts with the empty set is an increasing family. You get it, right? So by the way, a1 is a decreasing family. Now our vk is an increasing family. So by the previous theorem, we will have that the limit of vk as k was in infinity shall be equal to this union, just like before, right? So we are using this part here. All right. So now we need to remember that every vk is a1 minus ak. So this is equal to here like this, and that this limit is equal to the measure of a1 minus ak into infinity. All right. So now part of the hypothesis was that the measure of a1 was finite, so every measure is finite. If every measure is finite, then we have that this measure here is equal to a1 minus the measure of ak, because this equality holds whenever this is finite. So in particular, everything is finite, so this is also finite, so we have that here. So this is equal to the limit as k goes into infinity of this minus this one. So it happens that this is a constant term that we are subtracting from this sequence of terms. So you know that the property of limits is that if you have some constant plus a function or plus a sequence, then the constant can go out. So this will be equal to the measure of a1 minus the limit of this here by property of limits, right? Now we need to work this part here. So we need to do something here. And what is that? Well, I need you to remember that a difference of sets are kind of complements. So this thing here could be understood as the complement of a k. Its complement in A1, right? And you know how unions are behave with complements. So the union of these things will be equal to the intersection of AK and the complement of everything here, right? But the complement was subtracting A1 from this here. So we're subtracting our space out of this thing here. So this is equal to the measure of this. And you know that the measure of, once again, this the measure of A1 is finite, so the intersection will also be a finite measure. So this is getting a little messier. So this will be equal to the measure of A1 minus the measure of the intersection of every AK. So since these were all equalities, we have shown that this thing here is equal to this here. So if they are equal, then you can cancel these finite terms and conclude that the limit of this here is equal to the intersection here. But you know, since they were decreasing, this is a decreasing family, then this intersection is also the limit of the family. And that proves the theorem, the second part of the theorem. So it was kind of more complicated to prove, and we needed to use the previous part of the theorem. So to complete this lecture, we go with a final remark, and that is that suppose that our space, our X, is the natural numbers. So this is the set that starts with 1, 2, 3, and so on. So if we take an algebra that it is the power set of the natural numbers, you know that this is always a sigma algebra. And we define its some measure here on this algebra. And this measure is the counting measure. You know, the measure that assigns to every finite set its cardinality, and if the set is infinite, then its measure is the plus infinity. So given this is a measure space, so we can define a family here, a countable family here, such that each term of the family is equal to everything that starts from k. So this will be k, k plus 1, k plus 2, and so on. So we have that this family is an decreasing family. A1 is equal to the whole space, that is the natural numbers, and this contains A2, and so on, right? This is a decreasing family. But the intersection of every element of every set is, of course, the empty set, because in infinity you won't have any element, because if there's some element here, then that element is on AK, but let's say this, I mean, you have an element and here then this element is not in this other set, and this will be a contradiction. So this is the empty set, and you know that the measure of the empty set is 0. You know that, but it also happens that the measure of every AK is plus infinity, because every AK is an infinite set. So for our theorem with decreasing families, we'll have that, supposing that we apply this theorem, we wrongly apply the theorem, then we will have the plus infinity, the limit, because this is a limit of constant terms, everything is plus infinity, so the limit is plus infinity, would be equal to 0, because the measure of the empty set is 0. But what is failing here is that we are not considering this hypothesis that tells us that the first element is finite, and by that every measure is finite. So if this shows that this condition is necessary, right? So if you don't take into account this thing, then you will have nonsense like 0 is equal to plus infinity. So yeah, this is it for today. If you have any questions, you can write it down in the comments below, and I will try my best to answer them. We continue with the third lecture tomorrow, so see you around.